I need a real brainstorming session on how to start a video other than alrighty. Instantaneous power is the power at any instant in time. Good job, dog. I don't know if you can hear over the microphone, but my dog is losing its mind at the moment. It's just the state of being. So, instantaneous power is the power at any instant in time. And so, it is actually a function of time. P of t is equal to V of t, I of t. On the other hand, average power is the average of the instantaneous power over one period. So I'll call that big P. It's not a function of t anymore because I'm going to integrate the t out, but it's 1 over big T, the period, 0 to big T integral of little p of t dt, both of these powers are measured in watts. To get a clearer picture, what we can do is use a general passive linear circuit with a voltage and current. So let's let V of t be Vm cosine of omega t plus theta v, and I of t be Im cosine of omega t plus theta I. Then P of t is equal to V of t I of t, which is equal to Vm Im cosine of omega t plus theta v times the cosine of omega t plus theta I. So now I'm going to use a trig identity. That trig identity is the cosine of A times the cosine of B. That's equal to 1/2 the cosine of A minus B plus the cosine of A plus B. Alright, so that makes P of t be equal to 1/2 Vm Im times the cosine of theta v minus theta I plus 1/2 Vm Im cosine of 2 omega t plus theta v plus theta I. Now, if I look at this carefully, the first term here is not time dependent, and the second term is time dependent. And if I integrate that over one full period, what I'll find is that big P is just 1/2 Vm Im cosine of theta v minus theta I, which is equal to 1/2 the real part of V phasor I phasor complex conjugate. Before I can apply that to an example, I want to point out the following. A resistive load, in other words R, absorbs power at all times. While a reactive load absorbs, which reactive, by the way, is L or C. A reactive load absorbs 0 average power. Why? Because that reactive load is complex. So let's apply this to a couple of examples. Example number 1. Let's find the instantaneous power P of t and the average power big P if V of t is equal to 120 cosine of 377t volts. I of t is equal to 5 cosine of 377t minus 45 degrees amps. All right, so to solve this, let's start with P of t. I know P of t is equal to 1/2 Vm Im cosine theta v minus theta I plus 1/2 Vm Im cosine of 2 omega t plus theta v plus theta I, which is equal to 1/2 of 120 times 5 1/2 of 120 times 5 multiplied by the cosine of 0 minus negative 45 plus 1/2 of 120 times 5 times the cosine of 377 times 2, 754t plus 0 minus 45 degrees. So P of t is equal to 212.1 plus 300 cosine of 754t minus 45 degrees watts. The next part of this is to find big P. Big P is just 1/2 Vm Im cosine theta v minus theta I, and that's, I know, 212.1 watts. All right, let's apply that to a second example. Example 2. What I'd like to do in this example is I'd like to calculate the average power absorbed by Z equals to 20 minus J20 ohms if I have a voltage of 120 angle 0 degrees volts is applied. Alright, so all I need to do is I need to find I, so I can find out what theta I is and what Im is. So I is V over Z, which is 120 angle 0 degrees over 20 minus J20, which is equal to 120 angle 0 degrees. If I convert 20 minus J20, it becomes 28.3 angle negative 45 degrees. And so I get 4.24 angle 45 degrees amps. And then the power is equal to 1/2 Vm Im cosine of theta v, which is 0 minus 45 degrees. So that's 1/2 of 120 times 4.24 cosine of negative 45 degrees which is equal to about 180 watts. The last topic of this video is to talk, now that we have some information about power, about the maximum average power transfer. Maximum average power transfer. So for the maximum average power transfer, I need to set my load impedance ZL to be the complex conjugate of Z Thevenin. So RL plus JXL is equal to R Thevenin minus JX Thevenin. This is Z Thevenin complex conjugate if my Z Thevenin is R Thevenin plus JX Thevenin. I'm just taking the complex conjugate of Z Thevenin. So I want that to be the true value. And so when that happens, P max is equal to the magnitude of V Thevenin squared over 8R Thevenin. Okay, so the maximum value, the maximum average power transfer can be found by placing the load impedance to be equal to the complex conjugate of Z Thevenin, and I can find the value of maximum power by taking V Thevenin squared, the magnitude of it, over 8R Thevenin. So let's apply that then to example number 3. In example number 3, I want to find ZL for max average power transfer, and then find what is the max power or max average power. All right, here's my circuit. I've got 10 angle 0 degrees volts. I've got a 4 ohm resistor here. I've got 8 ohms. I've got a minus J6 ohm capacitor. I've got an inductor which has a value of J5 ohms, and then to that I have a load connected, ZL. All right, time to solve. So I want to start by finding out what Z Thevenin is. I turn off my source and I make the terminals an open circuit, and so I've got the following. I've got 4 in parallel with 8 minus J6 in series with a J5. So that is equal to J5 plus 4 in parallel with 8 minus J6, which is equal to 2.933 plus J 4.467 ohms. So I can answer the first part of this, which is what should ZL be? It's Z Thevenin complex conjugate, which is equal to 2.933 minus J 4.467 ohms. Next thing to do is to find V Thevenin. I go back to my original circuit and I make an open circuit at the terminals. And I'm looking for V open circuit. That's going to be equal to V Thevenin. This is 10, 4, 8 minus J6, and that's J5. Now, because that is an open circuit, there is zero current going through it, so J5 is, there's no voltage drop across it, so V Thevenin must live right there. So I can just use voltage division. V Thevenin is just equal to 8 minus J6, that's the impedances I care about, over 4 plus 8 minus J6 multiplied by 10, which is 7.454 angle negative 10.32 degrees. Now, I don't actually care about that. What I care about is P max, my maximum average power transfer, and that is the magnitude of V Thevenin quantity squared over 8 R Thevenin. Now, let's be really clear here. By R Thevenin, I literally mean the resistance part, the real part of this, not the complex part, just the real part. So that is equal to 7.454 quantity squared over 8 times 2.933, and that's equal to 2.368 watts. Now, before I wrap this up, I just want to highlight, I've been teaching this course for a really long time, and one of the most common mistakes here is not taking R Thevenin, but putting the whole Z Thevenin there. Power is a real value. It's measured in watts. That's what we're looking at. We care about the power. P max is a real value, and so I can't have complex numbers down there. I must be using the real part of, if I want, I could even say the real part of Z Thevenin. Okay, just to make that really clear, R Thevenin is just the real part of Z Thevenin. All right, that's all for this video. Thanks for watching. I only have one more video in this series about AC circuits that I'm going to cover. So thanks for watching so far. Hopefully you've enjoyed them, and you'll enjoy the last one. See ya.